So we're just going to review the software infrastructure that we've developed at Hopkins that is used in the dVRK, but it's also really a broader scope than just the dVRK. So the first question is where do you find it? And so nowadays, of course, it's on GitHub, and we've organized it through different GitHub organizations. The main ones are JHU cisst, which has the cisst software, as well as some, the electronics and firmware related to the dVRK. Then we had a number of reusable components that we called SAW. I'll explain more about that later, but that's in a separate organization just because there's so many of them. And then the dVRK specific software, uses a lot of components from these first two organizations, but the stuff that's specific to the dVRK is on this JHU dVRK organization. I want to mention there is there are at least several other repositories like JHU LCSR that has other LCSR software that isn't really relevant to what we're going to talk about today. We also at Hopkins internally have our own Git server, and we use that somewhat as a sandbox for developing things that sometimes make it out into one of these public repositories. So I added this slide recently just to try to explain kind of what are, I call it the requirements, but it's really more sort of the frame of mind we had back when we started developing this software, because we started, close to 20 years ago, maybe 18 years ago. And we were at that time, really focused, especially with computing hardware of those days, being able to get real-time performance, especially to do the typical kind of hierarchical multi-rate control you'd find in robot systems, where you're say servo control at kilohertz or more, sort of a mid-level control at really more like a few hundred hertz, and then you have your application, which generally is non-real time. And we were really focused because of trying to get this, high performance on being able to do these things multi-threaded in a single process. Although, we did realize that down the road that that multi-process, when you're building larger systems, you're going to need to also go multi-process. Another important factor for us was portability, because back then and still today, not everybody uses Linux. There are people who do system development on Windows or other platforms, including also real-time OSs like QNX, or, well, we don't support VxWorks, but as an example of another real-time OS. We wanted to also have this ability to plug and play devices, because we had a lot of different sort of tracking systems or robots, and we wanted to be able to reuse them in different applications in different ways. So that's basically the requirements. So just to present an overview of what the infrastructure, how it's organized, we have what we call the cisst libraries, and there are a number of different libraries here. Some of the key ones we'll talk about today are this cisst multitask, which enables us to create this component-based framework. I mentioned portability. That would be this OS abstraction library. There's a few others that may come up today from time to time. So that's these are libraries. And then given these libraries defining this component-based architecture, then we have a number of implemented reusable components that a lot of them are hardware interfaces, for example, interfaces to robots, sensors like force sensors, tracking systems, but it can also be software components, reusable software components. So that's the basic overview. This is a list again of the different cisst libraries. When we developed them, there weren't a lot of alternatives available open source, or we would have adopted them. There were definitely some things that were developed in parallel, and arguably many of these are more popular than what we've developed and are using. For example, on the mathematical side, many people use Eigen. There's also Oracos, this open robot control software developed in Europe that's relatively popular as well. So anyway, but this is kind of a summary, and this came straight off of the wiki page for cisst. So the documentation is also available there. So I'm going to explain now what we mean by component-based software. And this is perhaps the simplest definition of a component, that it's an independently deployable executable unit of composition. And for me, you know, actually as somebody who's really an electrical engineer, it's like computer scientists sort of following kind of electronics design principles, in that if you think of a software component as an integrated circuit, like a chip, that would be a component for an electrical engineer. And that chip has pins, which have, you know, inputs, outputs, or IOs, and you build systems, you know, with a small set, a small library of chips, you can actually build a lot of different complex circuits just by how you wire the inputs and outputs of the chip together. And so in my view, that's the way I would define component-based software. You have your software components and you're wiring them together. And I should mention, you know, this is something we certainly didn't invent component-based software. We sort of discovered it along the way as really fitting the type of development we wanted to do. And we're not the only ones. I mean, there were some early also works in component-based software for robotics. And then of course, ROS uses component-based architecture as well. So it's really very mainstream now to do component-based software development in robotics. Our view of component-based software, we looked at things called provided interfaces, where a component would essentially provide information, you know, an interface to another component, and then a required interface. That's basically what a particular component need, what services it needs. So you could think of it sort of like a client-server type of arrangement here. However, any component can be both a client and a server. It can basically require interfaces from some components and provide services to other components. So I mentioned also SAW. SAW is an acronym for Surgical Assistant Workstation. And the idea behind SAW was to be able, as I said, to reuse these components. So the idea being that the yellow boxes represent components that already exist and you can reuse, and then the blue boxes would represent components that that a user would develop for their application. So the idea is, you know, the application specific stuff is developed here, but then if you want an interface to a Novin Falcon, you use that interface component. If you want to talk to Slicer, you have Open IGTL link interface component, tracking systems, DaVinci's or dVRKs. You would be able to reuse those components. I don't have ROS on here, but ROS is a similar thing. One of these yellow boxes would be a ROS bridge to whatever other things you want to talk to over ROS. So I think this is the point where I switch over to Anton.
So when we started the dVRK code in 2012, we had all this infrastructure in place with cisst multitask and the component-based approach, so we decided to go for it. And here is a global diagram of what's happening on a modern dVRK process. And this is all single process, but multi-threaded. Each little black box is a separate thread. We're kind of lucked out on this architecture because when we designed the code initially was for Pentium 3, Pentium 4, we barely had a couple of cores, but now we have tons of cores. So the architecture is actually really taking advantage of the current systems. The thing that I want to show here is the IO, PID, ARM components have been there from pretty much from the beginning and slowly refined, slowly refining the approaches. One of the nice things here is you can multiply your number of arms without really expanding the load per core. So now we have one core per arm. That makes life very easy and to manage in terms of resources. This also facilitates the integration of Qt widgets that are running in separate threads. So you don't have what I've seen a lot with students have a single loop that says, refresh the widget, get the IO, do some computation, publish to ROS, subscribe from ROS, and then restart again. And then your IO control loop is bogged down by all this communication. This is not the case here. Everything is a separate component. So the IO and the computation is pretty much independent in terms of performance from what you do with the Qt widget and the ROS stuff. Where the modularity pays, and that's the next slide, is changing. So the second example that I want to show, the main difference is sitting here in the teleoperation component. Instead of using the IO, the PID that we had, we directly plug in a Sigma or any ForceDimension systems. And the dVRK code, we have now standardized interface for ForceDimension, but also the Phantom Omni if you want to do something on the cheap. And that is done just simple configuration file. And then you end up having the same graphical user interface, same ROS topics, everything is done by just swapping one component in the configuration file. So that has been really very useful for us to have a cheap dVRK platform. The other example that I want to provide is now you go back to the initial dVRK stack, but we wanted to talk to IGTL, which is OpenIGTL, which is the middleware, kind of the de facto standard for slicer. So if you want to do image guided stuff. And what we did here, you replace the code that sucks up data from the dVRK and send it to the middleware, or the other way around, gets command from the middleware and sent to the dVRK. By just replacing that component, you have the same code. And that's code that was kind of available in the dVRK from the beginning, but the last 2 years really paid off in cleaning up that code and having more standardized interface. We're going to talk about that a little bit more. The last thing was, and that you're aware of that, is 2 months ago, about a month ago, we were very confident that we could move to ROS2 fairly quickly because of the separation of the code. So the blue boxes and the gray boxes there have zero ROS dependency. They have a slight dependency using Catkin for building, but that's really just for convenience of using the ROS1 tool for building. The code dependencies are all in the yellow boxes. If I can rewrite the assumption was if we can rewrite the yellow boxes or orange boxes, we're going to be fine. And it turned out that even with affirmative interruption of user supports and everything, in about a week, I had a fairly solid new code for doing that. That means that was really where the component base paid off a lot. This is just a screenshot that I took. I posted that on the Slack channel to say, hey, look at that, I have ROS2, and I have it here. The other thing that I want to mention is all this bridging code that we have, that is for ROS, for IGTL, or anything, is independent of the device you put underneath. So now if you decide to use Phantom or any other force sensor that we currently support, or any other ARM that we currently support with the amongst the SO components, you can reuse all the bridges. So the good thing for me is my Omni, my ForceDimension, my Atraxis, my Polaris, because they are already SO component, the minute I have ROS2, they become ROS2 devices in about half an hour of coding. I need to rewrite the main, where I need to say, basically, I need to use ROS2 bridge, and the way I handle the ROS2 parameters are slightly different. So I can do that very quickly. Another side note on this one, this was actually running on Windows. So here it's a weird, funny case where you can run, if the core SO component is portable, which is the case for Omni, Atraxis, Polaris, and dVRK, now that we have UDP support, you can run that on whatever you want. So right now I can write the dVRK on macOS with IGTL, but with ROS2 being technically portable across different operating systems, we might have Windows SO component with ROS2 bridges. I'm not advocating for it, but if you have a hardware requirement for a driver that is only available for Windows, which some vendors still do, then that becomes really valuable. So that's one of where all this architecture seems cumbersome to create this provider interface, require interface, create this message passing. But once you've done it, there's a lot of leverage you can take on the libraries. I think at that point it was Peter taking back.
So I'll go over now some of the technical details behind the cisst infrastructure. First, just the difference between multiprocessing and multi-threading. I'll go through this kind of quickly, given the audience is familiar with software. But basically, there is a little bit of a debate in a component-based software community whether a software component must be a separate executable program. Is that really part of the definition of a component? And an example, of course, would be a ROS node. Each ROS component really is a separate executable, although they've added nodelets to try to take advantage of the multi-threading capabilities as well. We took the approach, or we have the belief that really software components do not have to be separate executables. They really are just separate threads that could be in one executable or in multiple executables. And that's really to be able to get this real-time performance that we were looking for. But we do have to be careful if you're doing multi-threading. You certainly have to be careful about things such as shared memory access. And then if you do want to use different executables, you obviously need some sort of middleware, such as ROS or OpenIGT Link. So this was really more for students who were maybe not so familiar with programming, about what were some of the challenges if you're going to be using shared memory, like global variables, to exchange data between two threads. You can, of course, run into problems if the reading thread is reading the global memory or the shared memory while it is being written. You can get some very inconsistent results that could cause really bad things to happen. So how do you solve that? Of course, you all know, you can use a mutex to restrict access to that, or you can use something like a mailbox or a queue to deal with that. So what we looked at was developing taking these types of concepts, although we decided not to use the mutex if we could avoid it, just to cut down. First of all, there's a little bit of overhead in invoking the operating system. And then secondly, with mutexes, you have, if things aren't done correctly, you have the possibility of deadlocks occurring. So we came up with a thread-safe implementation that's mutex free. And it works with basically using queues in one direction when commands are or messages are being sent from one task to another, but then also for the other direction, making data available through this state table. And so I'll describe these now a little bit more in detail. I guess one thing I want to point out on this slide is we actually created a new queue for every component that connects to another. I'm calling them tasks here, but the idea, these are the components. We create a new queue. That way, each queue has only a single writer. And so you can avoid issues with concurrent access to writing to the queue. So I'll mention the state table. The idea behind the state table is that each component maintains important data in that component. For example, if it's a robot component, important data would be things like the robot joint positions, the joint velocities, maybe the Jacobian, measured torques, things like that. And so those are saved in this table. And maybe it may be a little clearer to think of it as an array like this, where you've got basically at a particular time t, all of that information is stored as an entry in this table. And now time advances and you store another complete row of the table, and you keep going. Of course, we don't have infinite memory, so it's really implemented in a circular buffer so that at some point it loops around and starts reusing the memory. And so what the advantage here is that there's a single writer, that is the component is just writing things to the state table. So we don't need a mutex, but then you can have any number of readers from this state table. And this sounds a little complicated, but we used something called the command pattern, from the design patterns book to encapsulate all these details. So that at the client side, it looks really just like a simple read, a function read. So this is the component model that we have in cisst and SAW. As I've already described, we've got provided interfaces, which have the commands that you can invoke through this command pattern. There's also the possibility of generating events. And then on the required interfaces, we have what we call functions, which we use to bind to the commands, and then event handlers if there are any events coming in. I already mentioned the state tables. There's also a notion of state, what state the component is in, whether it's active or inactive. I'm not going to talk much about that now. I'm also not really going to focus on this, but for some of the video processing we did, there's a library called cisst stereo vision. We had these buffers with input and output interfaces to support these pipelines or streams for video processing. So this is the basic component. Most of the time we use, this is the base class. Most of the time we use things derived from a derived class called MTS task, which adds a periodic run method and adds a thread. This component actually doesn't include a thread. It's really just the focusing on the interface. And so the main components we have really that we use are derived from MTS task. It's either a continuous task, which is, as the name implies, continuously running, a periodic one, which depending on your OS, there's hooks to run it in hard real time if you're using something like Xenomai or QNX. And then we have a few others that are based more on event driven, either from a signal or a callback. And then I mentioned again this stereo vision thing that really is not going to be talked about today. So to show a little bit of code, if we look at the resource task, the one with the provided interface, it has these different commands it could provide. And then the required interface, I maybe should have called these functions because that's a terminology we use. But when we connect things, we bind one of these to one of these. And it's done based on strings, but that sounds very inefficient, and it probably is, but it's only done at connection time. Once the connection is made, things are done using, more efficient mechanisms such as pointers. And so this is what it would look like on the client side. I say, okay, I have a read function to read the measured joint state. I have a command or a void that I say just enable motor power. And then I add a required interface, and then I add these functions. And then on the other side, on the server side, I add my measured joint state to the state table, and then I define my provided interface, and I add these commands that make it give you very efficient encapsulated access to the state table in the case of reading the measured joint state. And in the case of enabling motor power, it actually behind the scenes has this queue and uses and basically reads from that queue to call and calls the appropriate method. In this case, a method of the server task called enable motor power. So the command objects we have are strongly typed. Some of the main ones are void, meaning I'm just sending, it's essentially more like almost like an interrupt. I'm just sending a command without parameters. Read is usually reading data from the server, like from the state table, although it could also be other types of reads. And again, write is like void. It's a command that's sent out with a parameter. And then qualified read is sort of a two-way thing, a read and a write. And I think this is where I switch over to Anton, because one of the, or soon, because really to get this working well, it's important to really standardize the command names and the actual parameter types. So you have plug and play. If I go back, you can see, I don't really say what the commands are, but there needs, or what the types are, but there needs to be a particular type associated with this variable, for example, the measured joint state. And then we need to have a name for it. In this case, we're using measured.js as the name. But those are the type of things that need to be standardized. What type this is, and then what we call it. So events are similar. It's just they go in the other direction. It's more like a ROS topic in that it's something that's emitted by the server or the task that has the resources, and it's basically sending an event to the client task. So I think this was the part where we was going to switch to Anton. And
yeah, so as I said, when 2012 we started the dVRK, we had the whole framework. What was lacking was an effort of standardization of the interfaces. When I showed the little component being replaced willy-nilly between a dVRK MTM arm and a ForceDimension haptic device, it didn't happen magically. I kept like changing the names here and there so that the interfaces would match. And what happened is in practice, even if you make your best effort to define an API, there are new cases that appear, and then you start having new names, and the names become too complicated. So here, what I want to show is a quick example of the dVRK, and I think some of your people have dealt with it and wondered what was happening. So the C code was initially, we had like get me the Cartesian position, and then there was a question: is it as measured by the sensors, or is it where the system is trying to go through the low-level controller, the PID, for example? And then we have a set position Cartesian, where it's like set that where you want to go. But is it something for the low-level controller, like the PID, or is it something for a trajectory generator? So we had the set position goal Cartesian. And then when Ross came in, Ross says, well, you cannot use camel case, you have to use snake case. So we changed it, and somehow we dropped the get in there. And then we added a more clear current versus desired. And so the name changed. And then when we wrote the Python client that was developed by a bunch of undergrad students to help us to work with it, you can see the name changed again. And at one point, you're trying to understand in your stack of code what goes where, and it became impossible. So what we had was an effort with, it's really strange, a joint effort with University of Washington and WPI to try to standardize a fair amount of commands based on use cases, and really focus on kind of like collaborative control until operation. So what we came up with, and to be honest, that was more under Peter's direction, the standardization of the operating state, and that proved to be very useful. I'm more of a student mind, like the robot is working and everything. If it doesn't work, we'll just stop it, restart it. So I didn't really care about that, but it turned out to be very useful. So the operating state is the robot enable, disable? Is it home, not home? This kind of little thing that the application needs to know before it can work with it, or can safely work with it. The other layer is the motion command, all this move, go somewhere, where are you, commands. And so we come up with this naming that is using the measure, the set point, the servo commands. I'm not going to expand too much in that because there's a whole wiki page for that. So one of the advantages of the CRTK also is now, if users tell me what is the API for the dVRK, I can redirect to the CRTK page that has all this documentation. And the same thing happened for the Omni, for my force sensor, for everything. So that's also a way of, by having the same convention, you factorize not only the code, but also the documentation and the knowledge. So when I go from one piece of code to the other, if I see somewhere servo CP, I know exactly what it means. I'm not going to double check everything.
Yeah, I wanted to, before you leave that page, I wanted to add one thing, or maybe two things. One is on the operating state. You know, we realize that robots, the state machines for robots are generally, or can be, much more complex than this. And so it's not to try to dictate that you need to follow a certain state machine for the robot, but rather to say, well, at the higher level software should have a sense for, you know, is the power on, or is the power off, or is there an error? And so we wanted, you know, you could have a state machine that has 15 different states in it, but the idea is that you could think of these as metastates. There might be several states where the robot is enabled or disabled. And as long as we standardize, say, well, if I ask you whether you're enabled or disabled, you can give me a yes or a no on that. That was the idea behind this, is sort of trying to provide a high level kind of categorization of what state the robot might be in. And then secondly, also on the motion commands, I'm not sure if Anton mentioned it or not, but the idea is not that every robot needs to support every command. It's just that if it does support a command, what is that command called, and what is its payload? Standardizing on that, but you don't have to, there's a lot of, position, force, types of velocity commands, and that may not be relevant to some robots.
So there's also a bunch of links in there, but I think most of you guys already have these links, and I think that was the end of the first, yeah.